company here in Portugal. And I'll be moderating a session on wave energy, building a new industry. We have a distinguished group of speakers with us today.
Can everybody hear me okay? Good. I'm actually not going to talk about EMEC. I'm actually going to talk about one of the barriers to testing, which is funding. EMEC has been instrumental in putting programs, funding packages and programs together to help get developers to access specifically the EMEC site, but also other test sites. So what I'm going to be presenting today is going to be about the Blue Gift and Innovation Fast-Tracked program that we were awarded and we're leading on that was started this year. So the project objectives is that this is a 2.5 million euro European Regional Development Fund program. The project aims to actually reduce those barriers to testing. It is focused on the Atlantic margin, so all of the companies that are participating and deploying, the consultancies, the supply chain companies that are trying to help these wave and tidal and offshore wind technologies get into the test sites. The duration of the project is 36 months. It just started this year. And we have 3 competitive calls, with our first call that has just been completed. It's a series of test site access vouchers, is what we call them, that actually gives the applicants support to testing of their devices and their subsystems. BMEP, which is located in the Basque Country, Plocan in Gran Canaria, Senoa in Bordeaux, France, and of course WavEC here in Portugal. So what we're really trying to do and aim is actually help the developers to reduce their access costs, so overcoming that barrier to testing, because it's very, very challenging to get into the sea to actually do this testing. So we have a minimum of 8 technologies that we're trying to focus on and support across these test sites. So here's the consortium. We have 7 test sites, as I mentioned, across that Atlantic arc. So EMEC all the way up in the north, all the way down to the WavEC site here, the Aquadora, I'm not going to say that right, test site here in Portugal. Somebody was actually helping me to practice that, and I still didn't get it right. I'll get it right by the end of the day. So we also have the next call, which is opening in spring 2020, but the first call has now been closed. So just to give you some background on, we had 10 applicants and 9 were actually successful. They are going to be testing at the SIMREV test site, the Senoa test site, BMEP, Agusadora, I did say that right. I did say that right. I knew it, I would get it right. And the Plocan test site. We also have Design Pro Renewables, Arrecife Energy Systems, Laminaria, Wello, Eolink, and SBM Offshore. These are the device developers that are actually going to be going to test at those centers. And also InterOcean, RW Power, and Wave Piston. So really the opportunity for these developers to get into those sites are now in preparation, so nobody's deployed yet. But we're actually helping them with their test plans, the consenting requirements, and some of the environmental monitoring activities that they may have to do to get them ready to actually deploy at those sites. So the next call, as I said, is opening in the spring of 2020. We're going to have a much larger program announcement about the call at the All Energy conference in Glasgow, which is May 13th. And so I hope that everybody can attend that. And I wanted to encourage, based on the past panel discussion and the challenges around supply chain, if in order to sit there and also reduce the barriers to testing, which is around funding, we also need to sit there and scale up with the supply chain. So I'm really encouraging that the next call is, instead of necessarily being led by developers, that we can actually see supply chain companies come through to help lead those projects and bring the developers along. Because I do think that it is fundamental that across all these areas that the supply chain continues to build because without them at scale, we're not going to be a successful global marine energy industry. So that's really all I have for my presentation. So just watch this space, and I hope to see everybody in All Energy in Glasgow next year.
Good morning, everyone. My name is, well, I've been already presented. I'm excited to talk to you today about DTOcean Plus, a project that I've been working on during last year. And if you're sitting here today in this room, chances are that you're very well aware of the potential of ocean renewables. When you're talking about wave and tidal, you're probably aware that it's clean, it's abundant, it's powerful, it's very widely available. You may also know that it's low variability when compared to wind. It can be accurately forecasted. And it can even be fit to respond to demand during nighttime. However, the ocean energy sector, faces some challenges. And the first is it's still low in maturity, well, especially when compared to offshore wind. The design process is also complex. We'll have some of the front runners talking about this today. They'll be able to talk better than me, obviously. But to design an ocean renewable energy system, you need to take a lot of variables into consideration. You need to take into consideration the selection of the site to harness the maximum power that is possible. You need to take into consideration the design of the PTO, of the device. You need to take into consideration the moorings or foundations, also designing for the specific soil. You need to design the energy transformation system to deliver the power out in the offshore to shore. And all of this amplified or aggravated by the fact that you're exposed to rough climates that affect reliability and ultimately costs. This is exactly where DTOcean Plus comes into hands. DTOcean is an ambitious project that is driven to accelerate the commercialization of ocean renewables. It's a 3-year project. It's a H2020 European project that started in May 2018 and will last until April 2021 with a total budget of 8 million euros. And it's basically an advanced open source set of design tools for selecting, developing, and deploying ocean energy systems. It also comes in the continuity of DTOcean 1, or DTOcean, which WavEC was also involved. Now, what are the objectives? The objectives are to support the entire technology innovation process, from the early concepts to the final deployment. And to do this, we propose a decision support software tool that will be professional, user-friendly, but also designed for different types of users. So we're talking about not only technology developers, but also project developers, investors, and policymakers. And we propose to do this at different types of aggregation levels. So we're talking about subsystems, device, but also arrays in mind, to make it freely available as open source, and finally to demonstrate it and push it to TRL 6 with demonstration scenarios of real cases. The list of partners is very extensive. We have many here. I'm happy to see many familiar faces here today that are representing our partners. We have 18 partners from 7 European Union countries and 2 leading partners from the US. This project is led by Technalia, and WavEC is leading some work packages and some specific tasks that I'm going to talk to you about now. So, what are the exploitable results? The tool itself, so we're proposing a tool, and the tool can be decomposed in several subtools. The first of the tools is structure innovation. And structure innovation is designed to identify and select new concepts and ideas, so to push innovation, to identify innovation potential. We have StageGate, StageGate tool, which is designed to help developers identify what is the stage of the technology, so which TRL your technology is, and how to push it to the next stages, what you should be focusing on, what should be investing on time and effort. Deployment design tools, which is basically it's for designing optimal solutions in terms of device and deployment arrays. And finally, assessment design tools, which are designed to evaluate the systems against many metrics that I'm going to talk to you about. All of this is supported by a digital representation. So the project is also involved in developing standards for data, for structuring the data related to ocean renewables. And this will lead the way to, in the end, we talked about this for offshore wind, to build digital twins for ocean renewable sector. Digging a little bit more into the deployment design tools in which we are, WavEC is seriously committed, the design tools will basically provide design solutions for ocean renewables, and it's decomposed in 6 modules. So the first module is site characterization to help do the site selection, to help identify good potential energy, and also to capture the information about bathymetry. You have many modules like energy capture, energy transformation, which is a PTO design, so help you test different PTOs, configurations, and try to understand what is the energy extraction. The energy delivery, which designs cables for transmitting the power to shore, and station keeping for moorings and designs, and finally, logistics and marine operations. Logistics and marine operations are something that we're at WavEC we're serious about. We're developing a tool for designing the logistics because the marine operations related to installation and maintenance, they take a big part of the costs of the project. So designing logistics solutions in terms of vessels, ports, equipment that minimizes the total cost of the project is something that has a lot of potential for ocean renewables. The assessment design tools, this work package is led by WavEC, basically consists in evaluating the projects in terms of performance and reliability, and also economics. It's 4 modules, obviously also environment. The first one is system performance energy yield. It's to evaluate what is the power performance. You have a module called HAMS for analyzing what is the reliability and what is the survivability of the project. System lifetime costs, which are developing in WavEC for evaluating what is the bankability of the project, how financially attractive the project is, and finally, environmental and social acceptance to assess the impacts on the society and in the environment. This is the progress to date of the project. As I said, it started in May 2018. We have 6 major milestones. We already achieved 3 of them. So far, we already refined, so we did a user consultation to refine user needs, to understand what the potential user could want with this project, with these softwares. We already defined the software requirements, how fast, what it should do, how it should operate, what should be asked to the user, what is reasonable to ask to different types of users. And we have defined already a digital representation of the ocean energy system. We have delivered 14 public deliverables, 20 in total, but until now 14. And during this month, we're going to start this in the slides. We have the next deliverables for which WavEC is committed to deliver. By the end, in 2021, we're going to have an open source, complete design suite of tools that will be available to the users for ocean energy. So what are the expected impacts? Designing ocean energy system is a complex process. There's a lot of intertwined variables associated with it. And our goal is to make it simpler. So within the 5 next years of completing the project, what we expect is, first of all, to push new technology to the market. This is our main goal. We are committed in reducing the O&M costs of the project. But finally, studies have shown that if we reduce the performance uncertainty by 40%, we'll be able to reduce the LCOE in 6 to 8% in the end of the project. So this is what we're committed to. Thank you for listening.
Will enable a deeply decarbonized future.
Thanks a lot. So Patrick Moller. So I'll speak a little bit about the technology and then the role we see wave energy can take in our future grids to provide grid balancing together with wind and solar. Corpower is a company we've been around since 2012. We're headquartered in Stockholm. We've been working here in Portugal from day one, actually. We do have an office in Oslo, and also we're hiring a Portuguese team right now. So we're matching well with the theme of the conference here today. And we do see a growing interest from utilities and oil and gas companies for the sake of balancing the grids with ocean energy going forward. You can say the challenge in wave energy that we face and everybody else face is basically to design a device which is robust enough to survive the toughest storm conditions, at the same time produce enough electricity to make it a viable business case. And the technical challenge which is out there is essentially that in the 50-year storm, there's a risk that you get so high loading on your device, you need to make it so large and thereby so heavy and expensive so that it doesn't match compared to the energy production you get. And that certainly has been the problem with wave energy. Devices have either broken or they've just not produced enough electricity compared to the amount of steel and concrete needed to make it a viable business case. And this is something we are certainly changing the picture of. And our solution to it is a new type of high-efficiency wave energy converters. This is the C3 half-scale device that we demonstrated in EMEC up in Orkney over the last year. This was a 25 kilowatt rated 4.2 meter diameter device. And we have introduced a few new solutions to wave energy. The first one, and possibly most important one, it's storm survivability. We have a new transparent protection mode. Here you see our C3 device operating in a 50-knot storm. You have 4-meter waves coming in, so equivalent to 8-meter waves in a full-scale device. And you can see how the buoy is hardly not moving up and down, is hardly not moving to the side. It's just sitting there. It's letting all the big waves pass by without reacting to it. So what we introduced here to wave energy is the equivalent of pitching down the blades of a wind turbine in storms. So we're letting the large energy flux of storm waves pass by the device without reacting to it. And because of that, we get very good survivability, and we don't need to design it with a large and heavy structure to take up the loads. We minimize the loading. On the other hand, it's a terrible wave energy converter at this time, since it doesn't react to the waves. So what we do in normal operational conditions, we use phase control technology to make the device resonant to the incoming waves. So here you see how the device is jumping in and out of the water. In a 1-meter wave, we may have the buoy moving 2 to 3 meters up and down. And this is actually based on 40 years of research in control technology from NTNU in Trondheim. So a lot of Norwegian R&D heritage going into our technology here. And in average, we're amplifying the power absorption of the device by 3 times over the year. In a small wave, you might get 6 to 7 times more energy with phase control, whereas in a bit higher waves, less than that. But in average over the year, 3 times as much energy for the same size of buoy compared to what was possible before without phase control. Inside the device, it looks like this when it's heaving up and down. And the magic devices that makes the phase control is the wave springs, which are cylinders sitting here to the side. And this converts the electricity and takes it down to the seabed through a cable connection in the middle. We've proven out over the years that in terms of getting more energy per the amount of steel and force, we have gotten more than 3 times as much energy compared to the force you need on the drivetrain. So you can see that as a metric of revenue potential compared to the cost of the drivetrain. And if you look at energy per ton, which is a metric of the revenue potential compared to the cost of fabricating your device, essentially we get more than 5 times as much. So we're bumping wave energy to above 10 megawatt hours per ton of device. And immediately that actually makes wave energy, I think, slightly more competitive than floating wind in terms of energy per ton. So we think it's a very promising future. We've proven it in quite a few stages. We still have 2 steps to go to take it to a commercial product, but it looks very promising so far. We've been following a structured product verification approach. So we started actually tank testing here in Portugal in 2012 and 13. Started a small scale and then gradually have increased the scale. We did our half-scale testing in stage 3 by dry testing in Stockholm and ocean deployment in EMEC. And now we are just starting the build of our first full-scale devices that we call the C4. This will be dry tested next year, and then we put it into the ocean in 2021. And we're going to get 1 cycle of learning on that device and then put 3 more C5 devices into a pilot array. So by 2023, we should have a certified and bankable technology ready for the market. And Corpower has invested quite a lot of efforts and money into dry testing capabilities. This is our current dry test facility in Stockholm. So the C3 device, before we took it to the ocean, actually went through a long rigorous test program where we started with low, careful, small energy, low movements, and then gradually stepped it up to full-scale storm conditions. And because of that, we could stabilize the device, fix any loose cable or any other software issue. And when we had the device out in the ocean, it really worked from day one. And that's a concept that we're planning to continue in full scale. We're building a huge test rig now in Stockholm that's going to be fabricated and put in operation next year. We also developed quite a lot on the installation and service methods. So we had the opportunity with the C3 device to do 3 rounds of deployment and retrievals. So by the end, we were down to about an hour of cycle time of installing the device in an automated fashion by winching it down to the connector and getting the electrical connection going. And we've demonstrated really the use of low-cost vessels in that. So through the half-scale program that was also supported by WavEC Scotland that is here today, we were able to prove the numbers. We could prove that the transparent protection mode really gives low loading in storms. We could prove the energy production numbers and the amount of energy or materials needed to it. And we can say today that we have a very clear path to get to competitive cost of energy when we scale up the volumes. We expect to be at 100 euros per megawatt with less than 400 megawatts installed in the market, and we can get down to 40, 50 by having a few gigawatts. We have a statement of feasibility from DNV since the half scale, and we're now going for full scale prototype certification. Our target now that we're working with is to do this 3-device demonstration, and really the Highway 5 program, as our new project is called, has been designed to get at least 8,000 hours of operation clocked on 3 devices, and then get certification on the availability and the production yield in order to be able to give warranty and become a bankable product to our customers. And the Highway 5 pilot array will look like this. Here you get a glimpse on the new technology coming out in the next years. You have the single C4 device connected up to a collection hub in the first stage, and then we're adding 3 more devices to that same collection hub. And the collection hub is designed for a 10 megawatt cluster in the end, which is the product that we're considering ourselves to develop. And it's designed to take 4 strings of each 7 devices into the floating collection hub there, and then an export cable going to shore. We see a very interesting opportunity with wave energy. It's a huge clean resource which is out there, but a very interesting aspect of it is the complementary production profile that we have to wind and solar. And just to give you some glimpse of that, we did a study here in California. Next year we need to come back with data on Portugal instead. But we simulated the installation of 6 gigawatts of technology here along the Californian coast on 4 places. We took all the production data of solar and wind from 2018, so the actual production each hour of the year, and then we simulated the wave production on an hourly basis. And then we could create plots to show how much more stable wave energy is. And a typical week, this is October 20 to 27th in 2018, had we had the same amount of wave as wind in California, in that you see the dark blue curve, it's the wave production, and the light blue is the wind, and the yellow, the solar. What is very striking is that wave energy is so consistent compared to the other 2 sources. On the short term, you can say that wave energy is much closer to a dispatchable or firm source, and that will become very valuable in the future grids. On the annual level, it also have an anti-correlated curve compared to solar and wind here in California. California has a deficit on clean energy in the winters, and we have a huge opportunity here for wave energy to fill out that gap by producing most in the winter months. And that is really driving a lot of attention from various customers around the world. And because of the complementary nature between wind and wave resource, there are multiple developers who are also looking into the opportunity of combining floating wind and wave arrays, potentially using the same export cable, potentially getting savings in capex because of that. You could think of using the same support vessels and service crews to get down the O&M costs. And that's a very exciting opportunity that we're working to explore with customers going forward. Thanks.
Okay, ladies and gentlemen, I represent AW Energy, which is a wave energy converter developer. We are probably more known from our product called WaveRoller. And this is how it looks. We are below the surface, catching the whole water column of the surge wave when it goes back and forth in the ocean. This is a nearshore device, so it's installed currently, for example, in Peniche in Portugal, 800 meters from the shoreline at the depth of 16 meters. So panel is the prime mover here. It catches the energy. Then PTO converts that energy to electricity and smoothens the peaky nature of the waves. And then we have the foundation, which both of these components are attached to. And also, this foundation is a very active part of our strategy of installation, submersion, and taking it up to maintenance. The working principle is basically very simple. The panel moves back and forth with the surge wave. We catch it with the PTO and use hydraulics to store and smoothen the energy, and then provide the electricity to shore substation. And of course, this is what we would like to see in the future, multiple devices working together on the shore line. AW Energy was established 2003, and we started working in Portugal in Peniche already 2007. So in very early stage, and I think we made a good selection there. The devices in the beginning were a bit smaller than today. Now I'm going to tell you a story about that starts 2014 when we were completing the grid-connected sea trials in Peniche, and it will continue hopefully far in the future. After completing the sea trials, where we got very valuable information of the loadings and of the functionality of the machine, and also the performance was validated by third party, DNV GL. We started designing the next generation WaveRoller. We first established full-scale PTO test facility on dry land. We started technology qualification program, certification. We got some money for that, and we got the design and the manufacturing certified, and now this year we installed the first of a kind WaveRoller in Peniche. So our demonstration unit in Peniche during 2012-2014 was a basic test platform for real marine experiments and gave us valuable data. We had 3 independent units combined into one platform. Then we established this dryland PTO test facility. We had 2 megawatts of our own test bench power, with which we could basically test all the relevant sea states, and also made a lot of reliability testing, structural testing, and also algorithm development for the capture of the waves. So this was very important asset for us. After the design has been completed and all the tests been done, we started the manufacturing of the first of a kind WaveRoller. Here you see the manufacturing of the PTO hull structures in Finland. All in all, we have parts and components from Finland, from Portugal, from Italy, from Turkey, from Canada, from UK. So we have really collected what we think is the best knowledge for each part. In the beginning of 2018, we started the manufacturing of the foundation in Peniche. This is a Norwegian design and manufactured by a Portuguese company. Here you can see the sections inside the structure that are gradually filled with water, and that is the idea of our installation and then taking into maintenance process. So we fill the tanks with water, one end at a time, to stabilize the structure, and then the reverse order, we fill these tanks with air to get it up. This way we can really use very small vessels for installation. Then we started to the transportation and unloading the components from Finland to Peniche. Here you can see the lifting of the PTO and a panel. Here you can see the final assembly of the panel and PTO to the foundation. The panel weighs something like 140 tons, and it's 18 meters wide, 10 meters high. This was done by Portuguese-Finnish cooperation, so we had Finnish assembly guys and Portuguese lifting company here to do the job. The PTO was done with the same crew. The critical part in this PTO installation is the alignment of the connection between the PTO and the panel. Then, of course, the substation is a very important part of the whole thing. This is a modular, portable substation, so it's made in a container. It was made in a container in Spain and transported to Peniche and installed there. And of course, the subsea cable installation was part of the job. It was done in September this year by a Portuguese company. And we had the cable reel on the shore and towed it with the winches out to the sea. And here you can see the part from UK, the subsea cable connector. Okay, after all the installation and assembly works, we finally got to the actual deployment phase. The deployment was done together with Portuguese companies. There were tug companies and a company that took care of the kind of control of the real installation procedure. Here you can see the connection of the subsea cable and then the actual submersion process that went quite far during that day. So anyways, the whole procedure, towing the device in place and submerging it, take about 1 day, meaning say 12 hours, and that can be substantially reduced by optimizing the procedures on the way. And of course, after working together the whole long day, it was time for toast. This is our Finnish-Portuguese crew, and they were working hard. Now the device is grid connected, producing energy. You can see the power output here in the middle. The power output from a single device is quite smooth, since we are doing the smoothening of the power output already inside the single device. The commissioning phase is going on, and we are optimizing the settings and the power performance of the device at the moment. Then, well, this is what happens with the foundation. So if the energy production doesn't work, well, we can grow seaweed and clams and crabs. This is something we should probably take a look in the future as well. The visual impact of the device is quite low. The very light white line you see in the middle of this video is the WaveRoller working in its installation place. And of course, in the future, we will complete our certification program. It has been quite rigorous and specific, so that is one part. The second part is, of course, completing the industrial processes and industrialization of the device. We already met the criteria for business interruption insurance this year, and these parts will be very important parts of the bankability of the technology. We have quite a big coverage of different global patents. Totally 79 patents either granted or pending. So we have protected our technology quite well, and more patents is to come. We are participating as a scientific coordinator in a EU Horizon 2020 project, WaveRoller. The goal there is to increase the power of the PTO and then, of course, reduce the levelized cost of energy in other ways as well. We have partners from Portugal, from Norway, from Finland, and from Germany, and in-kind contributions from UK. And we have quite rigorous plans to test our innovations. There are several hardware and software innovations, and at the moment, when the project is about halfway, it looks quite good, actually. Can we do it? Yes, we can. We have already very competent crew from Portugal, from Finland, from Norway, from Germany. So I think it's not a piece of cake, but anyways, we will do it. And referring to the what Patrick said previously, there is really an opportunity in the wave energy. I refer to the same kind of thing in California when solar and wind are not performing. Wave energy can fill the gaps and reduce the need for storing the energy. So we have a global opportunity. Let's do it. This is how we would like the future to look like. and let's say there is space for other solutions as well. Thank you.
Good morning, everyone. Thank you for the invitation to WavEC, providing the opportunity to talk about a realization of wave energy turbines in Portugal. This is basically the main focus of the activity of Kimaner. Challenges. It's probably the 5th time today that I hear about the challenges. So probably this is not going to be new. But I would like to draw your attention to something that has not been discussed here. Well, reliability. Everybody has spoken about that being one of the major problems in renewable ocean energy. Why is it ill addressed? Because there is a systematic tendency to test everything at once. And sea, or offshore especially, is probably the worst possible place to test everything at once. And we can only deal with that by simplifying and trying to make smaller steps. Because in fact, the failures of wave energy devices are well, we heard that this morning, the umbilical cable, major problem. So it's not the wave energy device itself, it's not the offshore wind platform or device itself. It's everything that goes around it that usually creates the most problems. I'm not going to talk about LCOE, of course, or the role or the stage where wave energy is still looking for the technology, the way forward, still being sought after. There is something that was not spoken, and it's quite relevant as well. One other challenge that will very soon come up, which is the LCA, the life cycle assessment. We, of course, are happy to deal with offshore renewables and what it means to a green economy, but there is a footprint on the manufacturing and the upkeeping, maintenance, etc., of the whole devices which cannot be overlooked. And again, against other renewable energies, wave energy does not stand out as well, very much like offshore wind. But the main challenge, the main goal or the topic of this presentation was efficiency. It deals with LCOE, naturally. So a more efficient device capable of producing more energy or converting more energy out of the wave resource will contribute to a better LCOE. And this is essentially a factor of two, in wave energy, a factor of two big components. Of course, we go beyond having selected the right place to install a device. Nothing to do with the actual efficiency, is what do we make with that power available. So the pneumatic conversion ability of the wave energy converter, so how much of that wave energy is actually converted by the converter. And finally, what is the real efficiency of the power takeoff unit. In the case of Kimaner, we're dealing with air turbines. And together with IST, Kimaner has a history of developing, building and testing wave energy air turbines, mainly of the oscillating water column principle, as the two that you see above. And the history is a very recent history. It's the company is 15 years old, but the first turbine that was built and tested in Ireland was an impulse turbine with moving guide vanes. The key features of that turbine are a very good operating range, unlike for the most famous Wells turbine that has a very narrow operating band, and the mechanical complexity, making it very good as a test, as a trial, very good as the demonstration of a concept, but very, very poor in terms of industrial future. The efficiency of that specific turbine was 55%. The next one, a different concept, a patent, a biradial turbine with an excellent operating range, very broad, across practically a five-fold variation of pressure available, having reached in tests both in an onshore plant in Motrico and in BMAP, in the Biscay Gulf, an efficiency of 62%. And 1 year, about 1 year and a half ago, Kimaner was challenged to look beyond the oscillating water column in search of this ultimate efficiency on air turbines for wave energy. And we were approached by a company, Bombora Wave Power, to develop a unidirectional turbine to be installed on a submerged membrane wave energy converter, specifically in Wales. Completely different approach. So the oscillating water columns are reciprocating airflow symmetrical rotors. So irrespectively of the direction of the airflow, they don't change the direction of the rotation as they would have to. But having a steady flow on a single direction makes these turbines like a gas turbine or an hydro power turbine in the working principle. This has led to an upgrade, let's say a step up on the efficiency available. All the values that I wrote down there are the average values. So for average wave climates, it's expected that, well, in fact, the other two above have seen figures that were better than those, 65 on one case, 70 on the other case, and expected to be 85 on the last one. So different direction, different approach. The first turbine was used in a test on a platform from Ocean Energy, and the graphs that you see underneath are the efficiencies that were measured on site during the actual tests. The only one that doesn't correspond to sea tests is the one on the right, because we have not yet had those sea tests. Actually, the device is being constructed now. Portugal is actually the only country outside of the UK where Bombora Wave Power has ordered equipment from. Our scope of supply is the whole PTO, not only the turbine, except for the generator that comes from a different company. And I will show you, I believe, in the following. No, not yet. Manufacturing a PTO. How can we make it a success story since we are building it here? Well, this, you may not know, but Kimaner is a company that is a mix between a academy, and industry in terms of its origin and still the way it operates. The amount of experience that come from both the academy and the industrial partners is significant. I may tell you that the youngest or the smallest experience of any one of its partners is 40 years experience. So a lot of things have gone across each one's desks. So we believe we do know how to actually approach manufacturing a new concept of any given mechanical device. And I try to write down here what I think are the key approaches. One thing is basically do not reinvent the wheel, but do not complicate anything unnecessarily, and make sure that you only choose design solutions that have proven manufacturability and assemblability. Do not complicate unnecessarily. Establish a sourcing strategy. This is key. We have to be clear on how are we going to source everything, the manufacturing, the purchase of the steel, the work preparation, how much do we put into the design documentation, how much work preparation do we embed in the design documentation. This has to do with building a supply chain and most of all developing a supply chain. We are all learning. So to assume that an industry, even the best fit industry in Portugal, is capable of interpreting drawings of something which is a new concept, it's completely new, and just make it right, this is not going to happen. So the most we can drive that path, if we have to design fabrication jigs, we do. If we have to specify exact manufacturing procedures, we do. And this is honestly the only way to develop a supply chain and to develop trust in that partnership. I will show you now something which is interesting, which is the welding assembly sequence of the PTO. This is a video courtesy of ASM Offshore Methods Department. Let me see if this works. What should I do to make it work? Yeah, it does work. What you see laying down on the floor is a jig, is a fabrication jig that we built. And what you see in blue is actually already the PTO frame that will tie up to the wave energy converter. The PTO itself will be appearing later on, right after, and it will fit this structure. The whole structure weighs around 70 plus tons, the structure and PTO together. This segment that you see here is the turbine, the generator casing, and the diffuser. And it goes on. I tried, when I was building this up, I tried to speed it up, but I couldn't figure out the way how to speed a video that had been done by a third party. So this is how the process, the sequence is, and there is a final duct segment that is going to appear now, which is used to close the whole thing. I am happy to announce as well that we have been invited by Bombora for their new project. This original one is 1 megawatt to be installed, tested in Wales. And there is, in the pipeline already, there is a new one with 2 megawatts. It will be a turbine of 2 megawatts. that currently is in the roundup of the partners. We were invited to become a partner. This is going to be installed in the Canary Island of Lanzarote, and is expected, this is what's interesting, in Wales it's a test, but here it's an attempt to replace, in the future, the fuel-powered energy production central of Lanzarote. So very high stakes, very high expectations. These are the consortium partners that we have been invited to belong to. So you see Kimaner, Engie, Enzen, Bombora, WavePower, Trelleborg, and of course we are proud to have been asked. Thank you very much.